So, today we will start fuzzy logic, okay? Logic that you know. Fuzzy logic and fuzzy systems. You know classical logic, I hope, classical logic, and from here this fuzzy generalization of this classical logic that we have already seen for set theory, fuzzy set theory from classical set theory. Okay. So, from where this we actually get this fuzzy logic. Okay. So, let us take one example. Suppose I am driving a car and you are driving a car. Okay. This distance you are driving and myself driving. Okay. Now, so if this is going one after another, so if it is closer and closer near, then you will brake. No. So, after means after how much distance you will apply your brake. So, if you have here classical logic, you see in classical logic the answer is either true or false, means your answer is true or false, 1 or 0, only two possibilities. Okay. Suppose I say okay, this distance is suppose 1 meter. So, if it is 1 meter, apply the brake. Apply the brake means either you apply the brake full 1 or do not apply. Okay. Suppose this distance is large. Okay. Okay. So, here also again you apply brake or not apply brake. Okay. So, that means here you have two answers, applying brake and not applying brake, that if I say 1 is applying brake and 0 is not applying brake, and again near or distance we have 1 or 0 again. You are seeing, means near, again near you cannot define. So, if it is near you will apply brake 1, if it is not near you will not apply. So, see either you have to full press, suppose this is 1 meter and you are here. Okay. So, now you will apply or not. So, you are understanding the means the benefit of fuzziness, and if you apply the brake suddenly, if you are near to that, suppose if you say near is okay, I have 10 centimeter near. So, at 10 centimeter you apply the brake, so it will what? You have accident. So, in fuzzy sense, so I can have slowly, means starting from point 1, point 2, point 3, point 9 and 1, when you are reaching here you are pressing the brake. So, because see these all are applied to your machines, suppose they are playing same there, those logics are there, means here you have, suppose I have from yes to no. So, in this suppose it is 1 or 0 whatever. So, yes to no you have 1 or 0. So, that means here in fuzzy sense if I draw this, so maybe here you have this 1 slowly, you are understanding, slowly it is coming 0. It is not that at a time you are applying. So, there are many applications. Suppose I want to mix hot and cold water, taking bath, okay, in the hotel you have hot and cold, but do not know how much cold, how much hot. Okay. Now, you have to mix these two, but how much? You have in classical sense only 1 and 0, either hot or cold. So, there also you see all these things you have the logics. So, that means in classical logic what we have the answers or the set values answers are 1 or 0, and here in fuzzy logic we have that means partial truth. Here you have either true, in classical you have either true or false, okay, but here in fuzzy sense I have partial true, partial false. Okay. So, before going into fuzzy logic, let us first revise a little bit about classical logic, then we will go to fuzzy logic. Okay. So, only keep in mind that here we have only true and false in classical logic, and some terms we will define here, okay, propositions etc., and then we will go towards fuzzy logic. Okay. So, for classical logic, I have already, I told that either true or false, 1 or 0. If I designate this as 1, this is 0. Okay? So, I can have, suppose this is an universal set, I can have a set A here, okay, and x belongs to A, suppose. So, either x belongs to A or not. So, again true, false, 1 or 0. Okay. Same propositions, if that proposition belong to A, if it is true, it will belong to A, I will have value 1. If it do not belong, means it is false, then it is 0. Okay. So, that means I hope that you know propositions, etc., because that is another subject, means what are the propositions, what are not. Suppose I write 2x plus 2 is equal to x, whether this is a proposition, whether this is a proposition, this is not a proposition, this is not a proposition, but if I write 2x plus 2 equal to x when x is equal to minus 2, this is wrong. But if this condition is there, then you have the answer whether true or false. If I write up to here, it is not a proposition. So, you can see other things about the proposition. So, keep in mind we have propositions. Suppose I have a proposition P, okay. I have a proposition P which belongs to this set A, means in set A it is there, okay. So, I can define its truth value T P, truth value of proposition P. So, in classical sense I have only two answers, either T P is 1 or 0 or 0, depends. Okay. Similarly, I can have its negation, means its complement or negation, T P bar will be 0. Okay. So, now you see I have simple propositions, I have compound propositions. So, you see when we drive again, suppose we drive car or something. So, if your distance is near, apply the brake, then apply the brake. Okay. So, this is one proposition and something. Okay. In airplane, if hot or cold and wind, then you take this decision. So, you are seeing you are connecting two propositions. Okay. So, if I have, so we have different connectives, okay, different connectives for these classical sense also, and those will again will extend to fuzzy sense. But let us do first for classical sense, so that you will understand what is that in for fuzzy. Okay. So, let us suppose we have x p such that x belongs to A. Okay. So, and we write T P as 1 if it is true and T P as 0 if it is false, remember that. Okay. Now, if I have another proposition Q and this is true when x belongs to B, and we write T Q is equal to 1 if it is true. Okay. Now, I have different connectives to connect P and Q. So, you know those things, those are this what? Disjunction, then conjunction, negation, implication, equivalence, these are main. Okay. So, one by one we will write. So, first one is disjunction, then conjunction, negation, implication, and then equivalence. So, I have disjunction, conjunction, negation, implication, equivalence. These are called logical connectives. These are called which connect two simple propositions and make compound propositions. Okay, let us see how these are defined next. Okay. So, remember this, x belongs to A and x belongs to B, P, Q, etc. Okay. So, let us start with disjunction. disjunction. So, we should have two propositions, suppose P and Q. Okay. So, disjunction actually OR, this is OR, this is the notation for OR. So, P or Q or P disjunction Q, this actually as per our definition that I wrote previously, that means X belongs to A or X belongs to, that you know. Yes. Then I can have your truth value of P or Q. P or Q is compound. So, truth value of P or Q defined by max, max of truth value of P and truth value of Q. No, not fuzzy, till now it is classical. See, because now Tp is either 1 or 0, Tq is either 1 or 0. So, whatever you can, sometime it is 1 0, so maximum is 1. So, that means this statement truthness is P or Q truthness is 1, if you get 1, if you get 0 it is false. We will take example, then it will be clear. Okay. Second is conjunction, and this is actually AND. Okay. So, yes, so we have P and Q, which is actually X belongs to A and X belongs to B. Okay. So, now truth value of P and Q I can write as, here this AND, so you know for AND it is minimum. So, minimum for Tp and Tq. Yes. Similarly, I can write negation. So, negation will be, if suppose your Tp is there, Tp is 1. So, Tp bar will be what? So, 1 minus Tp, that means 0, because it is in classical sense. Okay. Now, next important thing is your implication. Implication. Okay. Implication, that means P implication Q, and in the set form it is X does not belongs to A or X belongs to B. This is the definition of implication. What about the truthness? Truthness of P, T of P to Q implication will be your what? Truth value of P bar does not belongs to A union Q. Yes, or okay. This way we will find truth T of P bar union Q. Okay. Next is equivalence. So, here we have P, this is the symbol, okay, and if P imply Q, Q imply P, P equivalence Q. Okay. Here I can write truth value of P equivalence Q as 1 when Tp is equal to Tq, okay, and 0 when Tp is not equal to Tq. So, these are the 5 logical connectives for classical logic. Okay. Now, let us take one example and see what is happening. Okay. I will take for implication because it is little bit. Okay. Implication. Okay. So, suppose I have been given 4 propositions, okay, simple propositions. First one is if 1 plus 1 is equal to 2, then 4 greater than 0. Second, if 1 plus 1 is equal to 3, then 4 greater than 0. Third, if 1 plus 1 is equal to 3, then 4 less than 0. Fourth, if 1 plus 1 is equal to 2, then 4 less than 0. So, these are 4 different propositions. Tell me, out of these 4, which are true and which are false. Then we will do. First one is true, that is okay, but we have to see by implication rule. So, out of these, which are true, which are false. See, first 3 are true, last one is false. So, we have 4 propositions. So, among these, first 3 are true, last one is false. Let us see, okay, how it is done. So, let us take first one. Okay. For first one, what is that? If 1 plus 1 is equal to 2, although it is obvious, but let us see using your definition, then 4 greater than 0. Suppose this is your P, simplest proposition, this is your Q. I want P implication Q, P implication Q. So, see P, you are seeing this, for this P, truth value of P is what? 1, because it is true, and truth value of Q also 1. I want truth value of P implication Q, and you know by the definition that I had written. So, it is your truth value of P bar union Q, and you know this we write maximum of truth value of P and truth value of Q, because it is OR, because it is OR. So, I have maximum of truth value of P bar and truth value of Q. Now, truth value of P bar, because Tp is 1, so Tp bar is 0, Tq is 1, maximum is 1. So, 1 means it is true. Okay, understood? So, similarly, I can have third one, let us take third one, second you can do similarly, let us take third and fourth. Suppose I do third one, if 1 plus 1 is equal to 3, then 4 greater than 0. So, this is your P, this is your Q, sorry 4 less than 0, okay, yes, 4 less than 0. So, I have in this case Tp as 0, you are saying it is false. So, Tp as 0 and Tq as 0 or not? Both are 0, because both are false actually, if you see individually, propositions are false. So, I can have now T P implication Q, T P implication Q, and this is your T again P bar union Q, and then maximum of Tp bar and Tq, Tp bar Tq. Now, you see maximum of P Tp is 0, so Tp bar is 1 and Tq is 0, so this is 1. So, but you may see that both are false, so it should be false, but you see, but implication gives true. So, this gives it is. Similarly, you can do the last one is important, so I have to do. So, you have, suppose I take this as P, this as P and this as Q, fourth one, okay. So, you have Tp as 1, that is true, Tq is 0. So, if I want to find truth value of P to Q, this is your truth value of P bar union Q. So, we have maximum of Tp bar Tq, okay, and you see Tp bar maximum it is 0 and Tq is 0. So, you get 0 and so this is false. So, that means these 3 are true and this is your false. That means in implication if the first proposition is true, then your result should not be true. It is true, it is false, but the compound statement's truthness is false. You are understanding? So, this way we can have actually in control, a controller actually these are all used, okay. Fuzzy control till now when fuzzy was not there, so classical controller and all, okay. Okay. So, now we can write the truth tables, that also you can remember from your 12th class or 10th class, okay. So, let us write first for this implication, then both the other 3 is very easy, okay. Truth table for implication, for which 2 what? With 2 propositions, and because it is classical logic, so I have truthness as 1 or 0, true or false, okay. So, in this case, so I have suppose P, Q and P2, okay. So, these combinations how many will be there? Sure? 4. Let me write those, maybe this true, this true, this true, this false, this false, this true, false, false. These are the possibilities for 2 propositions, okay. True propositions, true, true, one or true, same, true, false, you have seen, that is false. True. This is your table, truth table. Now, you can do similarly if I have 3 propositions P, Q, R, and you can see what is happening P 2 Q, Q, T, R, whatever, okay. So, now in that case how many? That means what you are saying, it is 2 square, because you have 2 possibilities, 2 square, 2 cube, 4, 2 to the power 4, like that it will increase. You understanding? Okay. Now, truth table for others. So, if I have P or Q, so true, 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 false, true, false, true, true, false, false, okay. Now, I have suppose P and Q. So, this is your true, 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 false, 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 true, false and false, okay. Now, implication I already done, so equivalence. So, true, 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 false, because if you remember equivalence only one when Tp is equal to Tq. So, that means false, false will be true, others will be correct, okay. Similarly, I can have negation, negation only we have that you know already I have done negation. If you have P, P, so P bar only 2. So, if it is true it is false, if it is false it is true, that is all, okay. So, in this way you can have the truth tables, okay. So, we will do next class, okay. We will do next class about more on this implication.